Um, Last time we were discussing intermolecular forces versus intramolecular forces. Intra is within the molecules, and that is what we call covalent bonding last semester. Intermolecular forces are forces that exist between molecules and atoms. And therefore, because molecules are made of atoms and atoms are made of electrons and protons, every matter has dispersion forces. Some of them very strong, some of them very, very weak. The weakest of them all are the dispersion forces are going to be the weakest type of intermolecular forces, and those are due to the fact that matter is made out of atoms, and atoms are made of electrons and protons. So all the intermolecular forces are related to the protons and the electrons that are present within the atoms. And some of them will be polar and non-polar, and we're going to look at that. So these are the learning goals that we saw last time. We went through over, and these are the three things that I wanted to go in the first part. We talked about 10.1, 10.2, and now we're about to talk about polar molecules and their interactions. So let's go back. We discussed metallic bonding and ionic bonding. So you have questions on these, please feel free to let me know. So we discussed the different properties or how we should look at the different state of matter. And that's going to be important. These pictures here are going to be important because those are the pictures that we need to rationalize intermolecular forces and how they affect the phase changes. We're going to look at the phase changes later on in this chapter. So we talked about the size having an effect on intermolecular forces, and then we said that you can use the atomic weights to do the size. But that's the first approximation. All of these are spherical, so the contact between them is small. But when you have molecules that are bigger, are going to be different. So here's the dispersion forces for atomic ones. So maybe we should just put this one up here. Yep. So, and what happens is the electrons are going around these atoms, and they're neutral, they're not polar. But when they come in contact with one another, then let's say if this is the negative part, so the negative part gets attracted to the nucleus in this atom. And so there's going to be, instantaneously is going to be, if you think about the electron as a particle, that electron is going to be attracted to this nucleus. And so this part being positive is going to attract the electrons from this side, which is going to be there, and vice versa. So those are the London dispersion forces, and they are the smallest of the intermolecular forces. So London or dispersion forces, London forces or dispersion forces are the smallest type of intermolecular forces. They are only temporary, and they're induced to one another, because if you go here, they don't have initially any polarity, but they, to be able to interact and create that weak force, there's going to be a very small degree of polarization once they come together. Okay, so the polarizability of the atoms depends on the distance between the outermost electron and the nucleus. Remember, the nucleus is very small, it's in the middle of the atom. So the distance between the positive charge, which is in the nucleus, and the outermost electron is going to vary with the size of the atom. The farther the electrons are from the nucleus, the least attracted are going to be, and therefore they can be moved around by another atom or ion. And therefore, the larger the size, the more that atom is going to be polarizable. Okay, so shapes of the molecules also influence. And here we have all of these they have the same electronegativity, they're pairs, so they're non-polar. And again, the molar mass can be used to predict the relative boiling point. So a molar mass of 71 versus a molar mass of 160. 160 will have a higher boiling point. It needs more energy. The boiling point is the temperature, And the temperature, the higher the temperature, the more energy there is in the system. So once you give it enough energy, then you can start breaking apart the intermolecular forces between, let's say, bromine, once you get to 332 Kelvin. Okay. Interrupt me, please, if you have questions. Last time we also looked at this, and so it's not only molecular weight. All these three molecules have the same molecular weight, but they have different boiling points. So this one boils at 282, while this one here boils at 309. So this one is higher, and it's higher because there's more surface for them to interact. There's more atoms that are going to be interacting. Remember that London dispersion forces are atoms to atoms when they come together. So here, there's more atoms coming together than here when they touch. So, and the next slide shows you, oops. This slide shows you that the longer the chain, the higher the boiling point. Okay. I'm going back.
I had a question.
Yes, please.
For the boiling points, I was wondering why, when the mass is larger, why the boiling point is higher. If they're farther away from each other, shouldn't there be less force connecting them? So shouldn't the boiling point be lower?
Okay, so do you see my pointer right now on the screen?
Yes.
Okay, so I'm pointing to the center of the, let's go to iodine.
Okay.
Okay, I'm pointing to the center of iodine here. And the electrons, the outermost electrons are going to be here. So there's going to be a distance, which I am planning. So these electrons, when you compare them, let's say with these ones, which are going to be closer to the nucleus, the bromine or the iodine?
The bromine.
The bromine. So that means that the electrons of the bromine are more attracted to them because they're closer, and these are electrostatic charges. Remember, just like when you play with magnets, when you put them together, the closer you put them together, and the more they attract. So the electrons here of bromine, the outermost electrons, are more attracted to the nucleus than the outermost electrons of iodine. And therefore, the intermolecular forces is between one molecule of iodine and a second molecule of iodine. So when the second molecule approaches this molecule, it's going to bring its nuclei, and its nuclei are going to be able to distort this cloud more than a molecule of bromine interacting with another molecule of bromine. Why? Because when the molecule, the incoming molecule comes, it's going to be able to, it's going to come in the vicinity, and it's going to try to distort this electron cloud in here. And since this electron cloud in bromine is more attracted to the nucleus, it's going to distort less. If you go to iodine, it's going to distort more. And the more you distort the electron cloud, the more you're polarizing it. And so if you're polarizing, you're making it more polar, again, the electrostatics are going to be higher. So there are going to be stronger electrostatics here than here. Does that make sense?
Yes, thank you.
Okay. Thanks for your question. I'm sure you're not the only one who has that question. And I hope that you can, again, come and listen to it later on. Okay. So now when you have ion and a dipole, then there's going to be an attraction. An ion has either positive or negative charge, and a dipole has a positive and negative charge. So when that happens, you'll have a stronger interaction than just the molecules of bromine or iodine that we were looking at. Why? Because there's a full charge now in here, in the ions. The ions will contain a full charge. And the dipole is going to be also has a positive and negative charge. So if this one has, let's say, could have +1, +2, or -1, -2, the dipoles are going to have like 0.1, +0.1, or -0.1. So they're much weaker than the ions, but yet they have a side that is positive and a side that is negative. Okay, and that is obvious when you will look at the sphere of what is called the sphere of hydration. What is the sphere of hydration? When we do chemistry, we mostly use water as the solvent, and that means that molecules of water are going to be surrounding, when we dissolve things, they're going to be surrounding the molecules that, or the atoms that have dissolved, or the ions that have dissolved. So there's going to be, because the molecule of water is polar, it's not linear, it's bent, and therefore the polarity of the oxygen-hydrogen bonds do not cancel out, you are going to have molecules of water which are a dipole interacting with the molecules that have dissolved. And usually when something dissolves into water is because it's polar or because it's ionic. So again, if it's ions, you have ion dipole. If this substance that you dissolved into water and that is going to be surrounded by the molecules of water is a molecule, it usually has to be a dipole. In that case, you'll have instead of ion, you have dipole. So let's look at actual pictures, I believe, in the next slide. So, yep. So this is the slide, and this is for ions. So we're talking about ion dipole. So when you dissolve this ion, this is sodium chloride. It has positive ions and negative ions. The positive ions are going to be surrounded by the molecules of water, and they usually, because the atoms are they're not that far in size, really. There's usually about 6 that can fit around a single atom or a single. Now, if the ion gets much larger, it might be able to fit more, but in general, the usual number is 6, and that's the only number that I would like you to assume. If I don't tell you, you're going to tell me six waters. So every ion is going to be surrounded by 6 waters. If it's positive, notice that the oxygen side, the red one, is the one that is pointing towards the positive, which in the case of the water, the red end represents the oxygen, and that's the negative end of the molecule. The hydrogens on the opposite side of the oxygen, where the hydrogens are, this one here, they're going to be positive. So this end of the molecule is going to be positive, this end of the molecule is going to be negative. So is it going to reside on the hydrogens? It resides, when you're talking about molecules, it's best to just think about it just like a sphere. So on this side of the sphere, you have a negative charge. On this side of the sphere, you have a positive charge. So when you interact with an ion, depends on the ion exactly, there's going to be the positive end is going to interact. And sometimes it's going to be just the 2 hydrogens, sometimes just 1 hydrogen. So here they have all of them interacting with one of the hydrogens. And this happens when there's possibility of hydrogen bonding, then it becomes that. But if it's not hydrogen bonding, it not necessarily might be just 1 hydrogen, it could be more than 1 hydrogen. But that's what we have here, and that is fine. So this is the ion dipole. Why ion? Because you have positive ions and negative ions. Dipole, because the water is a dipole. So here you have, again, there are going to be an inner sphere of hydration, which is these 6 ions. But after that, there's going to be another layer and another layer of water molecules. But those are more fluid in the sense that they will go in and out of with the rest of the molecules of the water. So it's best at this point for general chemists to think that this is happening, and then these molecules can be substituted by molecules of the other molecules of the water. So, okay, questions? Okay, so we are looking here in this, we are looking at ion dipoles. There's also dipole that I mentioned. That's when you have actually molecular ions, excuse me, polar molecules. Okay. So let's look at the dipole now. And dipole is an interaction between 2 molecules which have positive and negative ends. The positive and negative ends are small. So if you look at these here, these lines, there's a delta minus and delta plus in this area. And delta means that there's a difference, a small, delta usually means a change. And because it's in lowercase rather than in uppercase, the delta in uppercase looks like a triangle. Here's a lowercase. That is telling you that there is a small charge. So it's not like it's -1 and +1. It's like 0.1, +0.1, and -0.1. So that generates an interaction between 2 polar molecules that align so that the positive end interacts with the negative end. In this case, you have HF, liquid, and therefore you're going to see that kind of interaction. You can see that kind of interaction also in the molecules within the liquid water. And you can see that the oxygen side of the molecule is interacting with the positive side of the next molecules of water. And therefore, the boiling point of water here, because this is an extreme dipole, which is called hydrogen bonding, and we're going to look at it later on, this boiling point is higher than HF. Although HF, it's higher in molecular weight, yet it boils at a lower temperature, and that is because the molecular weight you can use only when you have only dispersion forces. So if you don't have any other kind of forms. When you have dipoles, then that rule of the molecular weight doesn't apply anymore. Because the London dispersion forces are weak, these are much larger than that, and they are going to be the ones that are going to determine how much intermolecular force, total intermolecular forces there are within the molecules. The other example here is NH3, and NH3 also has hydrogen bonding, and so this dipole, again, the hydrogen is positive, the nitrogen is negative, it has a lone pair, so they form a dipole interaction. So for hydrogen bonding, which is the strongest dipole interaction, you'll have to have the one that is negative has to be a fluorine, an oxygen, or a nitrogen. So this negative part has to be only these three atoms. Fluorine, oxygen, and nitrogen. And also the hydrogen that is here, the positive end, has to be attached. This hydrogen here that is the positive end, because it's hydrogen bonding, has to be attached to an atom here. The atom here in the center has to be also fluorine, nitrogen, and oxygen. So there have to be either of those three in here plus either of these three in there. And then you are going to have hydrogen bonding. So you can have hydrogen bonding, for example, from a molecule of water interacting, the negative end interacting with the positive end of ammonia. And then you will have hydrogen bonding again. Okay. And the last one of these interactions is called induced dipole. In induced dipole, we kind of saw it when you have two neutral ones coming in. So non-polar, the atoms themselves polarize. This induced dipole will require a dipole and a non-dipole, or a non-polar. So molecule of water is polar, oxygen is non-polar. So you would say that it doesn't dissolve into water because non-polar substances dissolve into water, but some of them, and that's the beauty of water, water is able to dissolve sometimes things that are not that polar, that other substances cannot. And so here you see the negative end having polarized the oxygen molecule. So now this is slightly positive, this one is slightly negative. Notice that it's not red, so it's very slightly negative, and this is a slightly positive. So notice that this was kind of in between, and now it's not. So fish are very thankful for this. Actually, life in our oceans wouldn't be that abundant if this interaction did not exist, because otherwise oxygen will not dissolve into water, and oxygen will not be present in the oceans, which probably will limit the amount of life that we could see. Maybe in deep ocean water, there might be other kinds of life that do not need oxygen. But these ones, like most of the fish and the shellfish, will need this. Also, smaller animals. Okay. So here you have an example of a dipole. And when we look at this molecule, I would like you to look at, I don't know if I can maybe draw. Yeah, I would like you to just look at this molecule here. Yeah, it's not stained, but that's okay. No? Let me just grab it again. So it's CH3COOH. This is called acetic acid or vinegar in everyday language. And notice that it has an oxygen in this here, and it has another oxygen here, and a hydrogen. This hydrogen is attached to an oxygen, which will be the first prerequisite for there being hydrogen bonding. And it can interact with a nitrogen, oxygen, or fluorine. And this is an oxygen that has lone pairs, which means that this is a hydrogen bond. And not only can form one hydrogen bond, but it can form a second hydrogen bond. So although this molecule is very low in molecular weight, actually vinegar is not that volatile. Our noses are very, and our palates are very sensitive to vinegar because that usually signifies the composition of organic matter. And we have evolved to be able to tell when something goes bad. When wine goes bad, it tastes like vinegar and we don't like it. Although we put vinegar as in our, for example, in our salad dressing. So but it exists as a liquid and interacts with water as well, because there will be hydrogen bonding between this molecule and water. And so it dissolves into water. And so there, is not that much volatilized. Although if you smell vinegar, you can still smell some, because these molecules will escape also from the water. But small fraction, and but we can smell it very intensive. Okay. The other one here is going to be the interaction between molecules of ammonia, and you can see how they form a network. So ammonia actually, you can take an H3 gas and pressurize it very easily and transform it into a liquid. We don't usually work with ammonia because it stinks and is unhealthy to breathe. So we usually try to avoid ammonia gas. When we work with ammonia, we put it into water. And again, these molecules, because they have an NH and they have a lone pair here on the nitrogen, they can act as hydrogen bonding with water. Okay, so that was where we're supposed to be last time, but that's okay. Let's go in here, and we're going to look at what I was telling you about hydrogen bonding. So here we are in the periodic table, and this first column here of compounds is the carbon, nitrogen, oxygen, and fluorine. If you look at the periodic table, you have carbon, then followed by nitrogen, followed by oxygen, and then followed by fluorine. But notice that the oxygen is kind of out of order. And that is because oxygen is the best at forming hydrogen bonding. So it's so much better than actually forms a stronger hydrogen bond than even the HF. And therefore is a liquid at room temperature. If hydrogen bonding would not exist, water will only be found in the gas phase on the surface of the Earth. So it means that probably would have escaped our planet very early on, and we will have no water. Notice the big drop when you go from H2O to H2 down to a group. So this will be down the groups from oxygen downwards is going to be silicon. So this is H2S. This is HF, and this is HCl. So if you move to the next column here, this area here, you're moving down one box in the periodic table. Notice that all of them go down, which means that the interaction of the hydrogen bonding for this element is not that good. So again, we said NOF, so N, O, and F. So those are the ones that we are going to recognize as hydrogen bonding. Will Cl, for example, have hydrogen bonding? These ones will have very weak hydrogen bonding. So when in general chemistry, we say, no, they don't have hydrogen bonding. Although in reality, they do have very weak. I don't want you to know that. I want you just to recognize N, O, and F. Notice that when you move farther down from here, all of them start to go up again. And that has to do with the polarizability, because if you go from, let's say, you go from carbon to silicon, and from silicon to, I don't remember what comes out, a big line, but it's going to be bigger. A bigger atom is going to be more polarizable, and therefore it's going to have stronger intermolecular forces. So in this part here, they follow the molar mass, but not necessarily, because these ones are going to be fairly good dipoles, not only dipoles, but hydrogen bonding. And hydrogen bonding is what makes these three, instead of going downwards, it makes them go up. Okay. Hydrogen bonding is very important for life, DNA and also RNA, but this is DNA. DNA actually forms a double helix where all our genetic information is stored and all the information for life is stored. And that depends on hydrogen bonding. You should be able to recognize a hydrogen bonding here. You have a hydrogen that is attached to a nitrogen, NOF, and it's interacting with a carbon that has lone pairs of electrons, it's interacting with the oxygen that has lone pairs of electrons. And again, this is NOF, 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 a hydrogen. So this is possible. This is hydrogen bonding. So you should be able to recognize hydrogen bonding here, hydrogen bonding here too. NOF is N, NOF is N. So, and you have the hydrogen there. So again, you're going to see hydrogen bonding. And so when you look at the different bases that are making base pairs, all of them are capable of hydrogen bonding. Some of them 2, some of them 3. So when they have 3, they are actually the chain at that point, the 2 helices at that point are more strongly bonded. But at this point, the only thing I want you to recognize is to be able to tell me that there is hydrogen bonding in these interactions. I don't want you to memorize the DNA or the GC and TA pairing. We leave that for biology. So we have looked at most of them. We have looked at ion-ion pairing for ionic compounds, which is not here. Remember, I brought that from the next chapter. At the beginning of chapter 11, it talks about ions. So we talked about ions at this point. So we're covering 11.1, I believe. But these are the interactions. So ion-ion interactions are the strongest. Then will come the ion dipole. So this is an ion. It has to be a positive charge or a negative charge interacting with something that is polar. Hydrogen bonding comes next. Then dipole-dipole. Then dipole-induced dipole. And dispersion forces are the weakest. So that order of strength, I would like you to keep in mind and know. So you can do the analysis of comparing molecules later on how what are going to be the total amount in intermolecular forces. Usually the one that is on top trumps the one that is on the bottom. Although these 2 are very close, but this is an ion dipole, while the hydrogen bonding is still part of the dipole-dipole, but it's an extreme dipole-dipole, as you could see in 2 slides behind where we're looking at the graph and the different lines. Okay, please interrupt me if you have questions. I'm sure you have questions, so you're failing me. You need to interrupt me with your questions, please.
I know it's not like the necessarily same type of force, but covalent bonding in general would be like in between ion dipole and like ionic bonds in terms of overall like strength, right?
Yeah. Yes, you are correct. Yes, but that covalent bonding is considered intra means within the molecule. Yes, so these are intermolecular forces. But you are correct, very correct. Yeah, there will be ion will be on the top here, and then in between here where this line is, we'll have to put covalent bonding.
Okay. And then I think I already know the answer to this, but it's confusing sometimes. So in some biology classes, they make it sound like covalent bonds are stronger than like ionic bonds generally, but that's just because in like heavy water environments, ionic bonds don't hold up, right?
Ionic bonds don't hold up, correct. And that has to do with the strength of the hydrogen bonding and dipole-dipole. So they are the dipole-dipole interactions. As I mentioned, water is kind of a unique substance in terms that it's a very strong solvent. So we call it the ideal solvent, although some things don't dissolve. So it's not a perfect solvent for everything, but it does interact with a lot of polar and non-polar compounds. So yes, it's able to interact very quickly, very, very efficiently. It's a small molecule, so a small molecule it can get to interact. So when you look at this here, because it's a small molecule, you can put 6 around it. So all of those bonding is going to contribute. So it's like 6 times the effect, and therefore are able to break down ionic bonding more easily than the covalent bonding, because you cannot get 6 water around a single bond of a molecule of a covalent bond. Yes, good question.